So this is a follow-up video to my Coulombs Law video on electromagnetism. I'm going to do two examples here, and yeah, so let's just jump into it. First example, it says, okay, and a good technique whenever you're reading a problem is to write down your information given as you're reading it, and then read it again afterwards. But alright, so we have point charges of 1 microcoulomb and -2 microcoulombs are located at 3, 2, -1 and -1, -1, 4 respectively. So let's write what we got down in our first sentence. We have two charges. We have Q1 equals 1 microcoulomb, and then we have Q2 equals -2 microcoulomb, and Q1 is located at 3, 2, -1, and Q2 is located at -1, -1, oops, and -1, -1, 4. So the problem goes on to read, calculate the electric field on a 10 nanocoulomb charge located at 031 and the electric field intensity at that point. So we have a third charge, Q3, which equals 10 nanocoulombs, and it is located at 031. So how are we going to approach this problem? This is going to be, well, let's think about this. We have three charges, and if you remember in my last video I talked about superposition. I said that we would focus on one charge and then take into account all the charges around that charge. So in this problem we're focusing on charge 3 right here, and we're finding the electric force on this charge as well as the electric field intensity on this charge. So let's just write down our force equation. That's going to be some K is going to run from 1 to 2 because we have two charges here. So there's going to be, well, two other charges besides this one we're focusing on that's going to be contributing. It's going to be Q of the charge we have times Q of the charges around it, and then the of course the 4 pi, where's epsilon? Epsilon 0. We talked about what epsilon was in the last video, times r squared, and then oops, a sub r, where a sub r is the unit vector, capital R. Okay, so this is going to translate into, well, right away we just do one extra step to show this. We can basically we can factor out everything from this except for Q sub k. Well, except for r and r squared, because r squared is gonna differ, and you'll see why in a moment when I expand r squared, so to say. So in the last video we talked about what a sub r was, and how you can rewrite this expression here as the following. This is going to be r minus r sub k, and then magnitude, where's my magnitude? There it is. R sub k cubed. Now if you don't know why that's cubed, or if you don't know what went on here, watch my previous video. I'll put it in the description so you can see it. It says Coulombs Law. So That's why we couldn't factor out this r squared, because it actually has this counting mechanism k inside of it. So we'll just use this formula here to find the force. So the force is going to be equal to, well, we can keep this factored out, and it's going to be, well, q sub 1. Actually, we'll write it out explicitly so we can show each step here. Let me get minus r sub 1. Oops. And then this is 1. So I feel like this is more instructive to some people who might not be used to doing this type of thing. Alright, so we went through the summation when k equals 1 and 2, and these are the expressions we got. So now all we need to do is plug in. I'm just going to make a new line. So we're just going to plug in here. We have to, well, okay, so let me look at my notes here. We need to find, well, let's plug in our vectors. So we have 0, 3, 1. That's right here. That's this guy. That's going to be our first. That's going to be this r right here. From the geometry we went over in the previous video. So it's going to be. I'm going to write with the vector brackets. Vector brackets. Where are you? There you are. 0. Let me copy these vector brackets. There we go. So 0, 3, 1. Minus, now what's our r1? It's 3, 2, negative 1 from up here. So we have 3, 2, negative 1. Now we're going to plug in on this side. This r is the same, and this r2 is going to be negative 1, negative 1, 4. Negative, oops. Negative 1, negative 1, 4. And Q1 is 1 microcoulomb, or not microcoulomb. I think I said these are millicoulombs, not microcoulombs. And you know, I wrote down microcoulombs, but I think I said no. See, there I go again. I wrote down millicoulombs, but I said microcoulombs, and the astute viewer would immediately say, well, hey, where's the M? Because everyone knows micro looks more like this, and you'd be right. And so we're talking about millicoulombs here, not microcoulombs. So sorry about that. Okay, so down here is going to be the same vectors difference as up there, and we're going to copy this down. There we go. And our Q1 is 1 millicoulomb, or we can write it as 0.001 coulomb. And then Q2 is going to be 0.002, and of course negative. Let's put that in parentheses so we don't get screwed up here. We're kind of going off towards the side, but I'm going to make a new line and get rid of some of this stuff. So we're just going to do some simple arithmetic. So, you know, 0 minus 3. Well, let's get rid of this. Okay, so 0 minus 3, negative 3. Then we have where was I? 3 minus 2, which is 1, and then 1 minus negative 1, which is 1, plus 1, which is 2. Okay, so that's that up there, which means that's the same thing down here. This one is going to be well, 0. I'm looking down here because it's the same. 0 minus negative 1 is 0 plus 1, which is 1. 3 minus negative 1 is 3 plus 1, which is 4. 1 minus 4 negative 3. Gotta take those parentheses away. And this means that it's the same down here. So we got some, looks a little bit less convoluted now. The magnitude of this is going to be, remember, it's the square root of the sum of the squares. So there's going to be the square root of 9 plus 1 plus 4. So 14 is going to be the square root of 14. And the square root of 14 cubed is going to be 14 to the 3 halves. And let me write it like this. There we go. So let's see here. And this is going to be, well, we can simplify this to just be, well, this is going to be 1 plus 16, which is 17, and 17 plus 9, which is 26. So it's going to be 26 to the 3 halves. Okay. Now, let's see here. Oh yeah, we're good. Just had to refer back to my notes to make sure I didn't make any mistakes along the way, because that would be very bad, obviously. Okay, so, oh, and we can also plug in for epsilon 0. We can go 8.84, and then times 10 to the negative 12. And we can plug in for a Q, which is, I think it was 10 millicoulombs. 10 nanocoulombs. Yes, this one was nanocoulombs. The other one was millicoulombs. Alright, and nanocoulombs is 1 times 10 to the negative 9th. Oh, but this is actually 10 times 10 to the negative 9th because it's 10 nanocoulomb. Alright, so you basically you plug all of this in and you're gonna get where's my vector brackets? There we go. So we got negative 6.507. Then we have negative 3.713 and 7.506. And of course, another way you can write this is this a sub x plus well, it's actually going to be minus this a sub y plus this number right here a sub z. So either way, this is the answer for the force. This is the electric force on that point in millinewtons. This is in millinewtons. So you got to get some number. It's going to be in newtons, and you're just going to have to divide by 1,000, and you'll get this. This is in millinewtons. Let me actually. You should write these units down. Millinewtons. Okay. So, oops. Okay, so not too bad. You know, it's basically kind of plug and chug. There's a little bit of thinking in there. Next part is we got to get the electric field at this point. So remember, E is equal to F over Q. So it's basically all this divided by 10 times 10 to the negative 9th, and this turns out to be E equals, I'm going to write it in vector notation simply because it's easier, negative 650.7, then we have negative 381.7 and 750.7. 6.6, and this is in kilovolts per meter, because electric field units are volts per meter. So this is in kilovolts per meter. Okay, so that's the first problem. Let's move on to the next one. This is pretty kind of an interesting problem. This next one, it's let's turn the page. It is all right. So we have actually I drew a little picture here, and let me center it better in Paint. We have this little thing going on here. Two masses that are charged on two strings, and their charge is keeping them separated. Basically, they're hanging by gravity, and the charge between them is pushing them apart, so they stay like this. And we want let's read the price. It says 2-point charges of equal mass m. So that's these two guys, A and B. Okay, and charge Q are suspended at a common point by two threads of negligible mass and length L. Show that at equilibrium, the inclination angle of theta in our case, of each thread to the vertical is given by, and then they give an equation. So we're going to find the charge. We're going to find. Well, let's see. We're showing that we're finding the inclination angle when theta is very small. So let's go through this. Basically, let's get my little arrows here. You're gonna have these are both the same charge, so you have an electric force going this way. These are my little vectors here, and then you have equal and opposite. Oops. Wrong arrow. You have an equal and opposite electric force going this way from that one, and then you have, of course, you have mg. Oops, that's not really centered. Oh yeah, I forgot I can move it. This is like the new Paint. And then you have, well, it's not so new anymore, but you know. Then you have that vector. So this is the mg. In fact, let me label this. This is mg, and this one is also mg. Oops, mg. And these two forces right here are the same. They're equal and opposite electric forces. So it's gonna write Fe and Fe. Okay, so there's obviously going to be some trigonometric math going on here. So let's bring up our math page. We're going to get alright, so there's tension in the string here, and well, I can't draw one of those arrows because it doesn't have a diagonal. I'm limited by Paint here, folks. So let me just make a thick line. There's going to be a tension here on the string, and then similarly for the other side, there's going to be tension on the string, and we have to just, you know, decompose all these. So we have we're going to get T sine, where T is tension, T sine of theta equals Fe, and we can see that here because this is theta and the sine is going to be this, and it has to be equal to this. So that's in the horizontal direction, and then we're going to get T cosine of theta equals mg. And by the same logic, that's the vertical component of the tensile force, and it's equal to mg because it's in equilibrium, so they have to be equal. And this is just basic summing the forces in the x and the y direction. So these videos assume that you've summed forces before, because technically you have to take mechanics before electromagnetism, but so you should be good with that. And I'm probably gonna make a video later on showing how to do that stuff. But so if we divide the first one by the second, the t's, the tensions, are gonna cancel, and we're gonna get sine of theta over cosine of theta equals Fe over mg. And well, what's Fe? Fe is just was going to be q squared because they're the same charge, and it's going to be 4 pi epsilon 0 r squared, because that's the formula for the electric force. But if we look here, let's see, this distance, well, let's label this distance here. The distance right here by this gray line is going to be given by r. That's the distance between the two charges. So if we look here, it's going to be, by the geometry, it's going to be L 2 times L sine of theta. That's right. R equals 2L sine of theta. So we plug in everything here. There's going to be tangent of theta equals, plugging in this is going to be 4L squared sine squared theta. And, well, these 4's are going to combine to give 16. And, let's just bring this mg inside here. Okay, and now we're going to solve for q. Make a new line. Solve for q. Bring this over. And q squared. Oops. Squared. And it's going to be... I'm just doing some rearranging. Okay. Well, I don't think that was really necessary, to be honest with you. Yeah. Oops. Square. Okay, so this is our q that's given, and actually I'm going to move the q over. So this is one of our goals. It might not have been clear in the beginning. This is one of our goals in the problem, to find q. So that's the q that we're getting, and now we're gonna try to find we're gonna find the angle when theta is really small. So when theta is really small, sine of theta is approximately equal to theta. And it's also approximately, theta is also approximately equal to tangent of theta. And you can do this by expanding them in their Taylor series, and just taking the first couple of terms. I'm not going to go through that now because I feel like it would be counterproductive. It might be more confusing than it is good. Convince yourself. In radians, and again I stress, in radians, plug it in your calculator. When theta is really small, these are all basically the same value. So what you're going to do is you're just going to replace sine and tangent with just theta. So it's going to become theta cubed. And then you got to solve for theta cubed. Let's move theta to the other side. Oops, that's going to be cube root theta equals that. So that's our theta. And let's just box in these answers. That's basically it. Those are the two problems. Thanks for watching, you guys, and I will see you later.